Good morning or afternoon, depending on where you are. Welcome to the third of 4 webinars on preparation for the C3 Advanced Surveying exam. I am Kevin Jones. I'm the examination administrator for CBEPS, and I'll be the moderator for the session. And the presenter is Dr. James Secord, professor at the Geodetic and Geomatics Engineering Department at the University of New Brunswick.
Okay, thank you, Kevin, and good day to everyone. Here is my version of the agenda for today. If you have been to any of the previous sections, most of this will look rather familiar. A bit of a preamble as to what we are expecting the participants to have already done before they come into the sessions. We've had 2 sessions already, and I'll come back to these 2 once I've gone through the session for today, which is so I'm now going to make a few comments regarding the list that's in the learning outcomes. So, Anonymous 2002 is an engineering manual from the U.S. Army Corps of Engineers, which is available as a PDF to download, and it is a very comprehensive overview of a lot of the material that's in this particular portion. KISM 1956 is now available on the CBEPS website. It's a chapter out of a book. It may look to be a bit ancient, 1956. However, it does deal with the fundamentals of the process referred to as optical tooling, where we take instruments very similar to our surveying instruments. In fact, the major one is called a jig transit, which on first look would resemble one of those old 4-foot screw transits that your employer probably learned. However, they don't have any horizontal circles. Basically, the difference between them and a surveyor's transit is the fact that the telescope has a much shorter focusing sight, down to a few inches, and it is very good with its accessories at creating right angles. So you can generate vertical planes at right angles to reference lines and that sort of thing. So optical tooling is basically a process by which they can take a 3-dimensional problem and reduce it into offsets from planes and lines and that sort of thing to very high precision, but usually over a fairly limited extent, rarely over 100 meters or so, but better than 1/1000th of an inch or 0.025 of a millimeter. The next one is Chernovsky 1993. And these are listed not necessarily in alphabetical order, but the order in which you should be consulting them. Chernovsky's 1993 paper is a general overview on both mining surveying, which is the topic of the next session, and engineering surveying, which in this particular instance was targeted at civil engineers. The next one, Chernovsky and a few others in 1991, is Chen, Secord, and Zostak Chernovsky, and it deals with what's maybe one of the major topics of today's session, and that's when we normally do surveying, we do it to coordinate points. But if we do the repetition of a survey, we come up with a second set of coordinate values. And comparing the second set to the first set, we can, to some extent, describe how certain points are moving. But that isn't such a straightforward process, and that particular paper deals with it in the context of monitoring a sensitive structure like a hydroelectric power generating station, but there are other applications of it. La Chapelle, and a few others, there are 2 papers, one 1984 and the other 1988, which to some extent are really more for underground surveying because they deal with tunneling, but it's also an interesting aspect that it deals with measurements of high precision, although they are under the constraints that we would normally encounter in underground surveying. But it's also an interesting example of before and after the use of GPS. The one by Robinson and a few others from 1995 is a very good example of, even though it's 1995, is really a reflection of the current capabilities of instrumentation. Precision total stations of the highest possible precision, and all the techniques that are involved with that. That was in the context of the superconducting supercollider in Texas, which was really a combination of engineering surveying, metrology, and tunneling. And then we have a paper by Whitaker in 2000, which comes back to the deformation monitoring process and the capabilities of robotic total stations being able to do things and the consequences of trying to do measurements over an extended period of time. The major culprit, the major problem with it is dealing with the effects of refraction, both vertical and lateral refraction. And then the last reference is an indication of how we can take our ordinary surveying measurements and marry them very nicely with other information. So it goes beyond just surveying and the analysis of surveys, but the fact that in most instances when deformation monitoring is being done, it's attempting to match or verify or improve the modeling that's done by other types of engineers like structural engineers, geotechnical engineers, and that sort of thing. So it's dealing more with the mechanics of the deformation. This may not seem directly necessary, but understanding a deformation mechanism and how it's going to be reflected on the surface of a sensitive structure allows us to decide on what surveying measurements would have to be done. So those are the essential reference material items that I suggested would pertain to this particular session, and as you already see, they sort of overlap into the next session, underground survey. And to some extent related to this particular topic area are the study questions that are listed there. So I guess my first thought would be to see whether you have any particular questions upon which we might focus. If you go through the learning outcomes section, you'll notice that there are certain recommended prerequisite knowledge, and this is given a little bit in the preamble here under section 3.1. Syllabus items C1 and C2, you should be very comfortable with both of those, particularly to be able to do derivatives. And I guess in order to do that, you have to be able to put together the formula or recognize the formula as it's given at the back of the examination questions, do the partial derivatives, and use that as a basis for the propagation of uncertainty. And we have two instances where that can happen. One of them is the straight propagation of variance, where a variable x is a function of a variable y, and it could be a vector as it's shown there. We put together the relationship and use that in a matrix form to propagate the uncertainty.